Out there, beyond the orbit of Mars, beyond the scattered rocks of the asteroid belt, a giant hangs in the darkness. Jupiter orbits the Sun at a distance of 778 million kilometers. That's 5.2 times farther from our star than Earth. At that distance, sunlight takes 43 minutes to complete its journey, arriving as a whisper of the radiance that warms our world. And yet, despite this remoteness, despite the cold and the dark, Jupiter dominates its region of space with a quiet, overwhelming presence. This is not a world of rock and metal. Jupiter is something else entirely. It is a sphere of gas and liquid, hydrogen and helium, swirling in patterns that have persisted for centuries. Its equatorial diameter stretches 142,984 kilometers across open space. To put that in perspective, you could line up 11 Earths side by side along Jupiter's equator and still have room to spare. The volume tells an even more extraordinary story. Inside Jupiter's boundaries, you could fit 1,321 Earths. Not lined up, but actually occupying the same three-dimensional space that Jupiter fills with its gases and storms and hidden depths. For the next 2 hours or so, we're going to explore this giant world together. We'll move slowly through the facts, through the measurements, through the quiet details that astronomers have gathered over centuries of patient observation. There's no rush here, no urgency. Just a gentle journey through one of the solar system's most magnificent structures. You can close your eyes whenever you want. You can simply listen, letting the words wash over you, allowing your mind to drift among the cloud bands and auroras of this distant planet. If you fall asleep along the way, that's perfectly fine. The universe will still be here, still turning, still glowing in the darkness. Jupiter doesn't shine by its own light the way our Sun does. It lacks the mass necessary to ignite fusion in its core, but it does emit more energy than it receives from the Sun. Deep within its interior, heat left over from the planet's formation continues to leak outward into space. This isn't the fierce nuclear burning of a star, but rather the slow contraction of Jupiter itself, releasing gravitational energy as it gradually, imperceptibly shrinks. Each year, Jupiter compresses by approximately 1 millimeter, a measurement so small it would be impossible to notice even if you could somehow stand at a fixed point in space and watch the planet for a human lifetime. Yet over billions of years, this gentle contraction has been sufficient to keep Jupiter warmer than it otherwise would be. The planet's average density is only 1.326 grams per cubic centimeter. That's barely more than water, which sits at 1 gram per cubic centimeter. Earth, by comparison, has a mean density of 5.52 grams per cubic centimeter. This low density tells us that Jupiter isn't made of rock and iron the way our planet is. Instead, it consists primarily of the lightest elements in the universe. 76% of Jupiter's mass is hydrogen, 24% is helium. Everything else, all the other elements combined, carbon and oxygen and sulfur and neon, water vapor and ammonia and methane, makes up less than 1% of the total. This composition mirrors the Sun itself, which formed from the same cloud of gas and dust that gave birth to Jupiter and all the other planets roughly 4.6 billion years ago. In fact, Jupiter contains more than twice the mass of all the other planets in the solar system combined. If you were to gather up Mercury and Venus and Earth and Mars, all the asteroids, Saturn and Uranus and Neptune, all their moons, every ring particle, every comet, every speck of matter orbiting the Sun, except for the Sun itself, and Jupiter, Jupiter would still be more massive than all of it. together. 317.8 times the mass of Earth concentrates in this single sphere of gas. Despite this tremendous mass, Jupiter is not the densest object in the solar system. Far from it. The low density means that Jupiter is mostly empty space, at least in the way we usually think about solids. There is no surface to stand on, no ground beneath your feet. If you somehow descended through Jupiter's atmosphere in an imaginary spacecraft, you would never encounter a moment where you transition from gas to solid. Instead, the atmosphere would simply grow thicker and thicker, denser and denser, the pressure mounting around you, the temperature rising, until eventually the hydrogen itself would be compressed into a liquid, and then, deeper still, into a state we call metallic hydrogen, where electrons are stripped from their atoms and the material conducts electricity like a metal, even though it remains a fluid. Jupiter's gravity at the cloud tops, at what we might loosely call its surface, is 2.53 times stronger than Earth's gravity. An object that weighs 10 kilograms on Earth would weigh 25.3 kilograms on Jupiter if you could somehow place a scale there in the turbulent atmosphere. But again, there is no there. No place to set down a scale. Just layers of atmosphere growing denser with depth until the very concept of atmosphere ceases to have meaning and you find yourself in an ocean of liquid and metallic hydrogen extending down toward a core that may or may not exist in a clearly defined form. We're settling in now. Finding our rhythm. Jupiter doesn't demand your attention the way a sudden storm might. It simply exists, vast and patient, turning slowly in the outer solar system. In the next sections, we'll explore different aspects of this world. We'll talk about its age, about the fact that it formed before any other planet. We'll discuss its rapid rotation, which creates the fastest planetary day in the solar system. We'll examine its bands of clouds, its great red spot, its 4 large moons discovered by Galileo more than 4 centuries ago. We'll venture into its magnetosphere, the largest structure in the solar system apart from the Sun's own magnetic bubble. And we'll consider the brilliant auroras that dance continuously above its poles, hundreds of times more powerful than anything Earth produces. All of this will unfold at a gentle pace. There's no test at the end. No need to remember specific numbers, though the numbers themselves carry a certain quiet beauty. This is just an opportunity to let your mind wander through the cosmos, to contemplate scales and durations that dwarf human experience, to rest in the knowledge that the universe is far stranger and more magnificent than our daily lives usually allow us to appreciate. When we describe Jupiter's size, we often fall back on comparisons to Earth, because Earth is the scale we understand most intimately. But even with that familiar reference point, the numbers can feel abstract until you really sit with them. 142,984 kilometers. That's the diameter measured across Jupiter's equator. For context, Earth's equatorial diameter is 12,756 kilometers. Jupiter's diameter is 11.2 times larger. If you could place Earth next to Jupiter, like 2 spheres on a table, Jupiter would tower above it in every dimension. But diameter only tells part of the story. Volume grows as the cube of the radius, so when you increase diameter by a factor of 11, volume increases by roughly 1,321. This means Jupiter's volume is 1,321 times greater than Earth's. Imagine filling Jupiter with planet Earths. Not compressing them or changing their size, just packing them in like marbles in a jar. You would need 1,321 of them to fill the space Jupiter occupies. And yet, despite this enormous volume, Jupiter's mass is only 317.8 times that of Earth. This seems like a discrepancy until you remember that mass and volume together determine density, and Jupiter's low average density reflects its composition. Hydrogen and helium, the two lightest and most abundant elements in the universe, make up the overwhelming majority of the planet. These are the same elements that fuel stars. In fact, if Jupiter had been about 80 times more massive, it would have achieved the necessary core pressure and temperature to begin fusing hydrogen into helium. It would have become a star, the solar system's second sun, and the entire architecture of our cosmic neighborhood would be unrecognizable. But Jupiter didn't quite make it. It gathered enough material to become enormous, to become dominant, to shape the orbits of everything around it, but not quite enough to ignite. So it remains a planet, albeit one unlike the inner worlds of rock and iron. It remains a failed star, some have said, though that phrase carries an unfortunate connotation. Jupiter isn't a failure at anything. It is simply what it is. A gas giant, the largest example of its kind in this solar system. A world where hydrogen reigns and pressures deep within can transform that hydrogen into states of matter we've never reproduced on Earth. The mass figure bears repeating because it's central to understanding Jupiter's influence. 1.8986 times 10 to the 27th kilograms. Written out, that's 1,898,600 billion trillion kilograms. Earth, by comparison, has a mass of about 5.97 times 10 to the 24th kilograms. Jupiter contains more mass than all the other planets combined, and then some. Mercury, Venus, Earth, Mars, the asteroid belt, Saturn, Uranus, Neptune, every moon, every ring particle, all of it, together adds up to less than half of Jupiter's mass. Jupiter alone accounts for more than 70% of the planetary mass in the solar system, excluding the Sun. This massive concentration of matter creates a gravitational well that has profoundly shaped the solar system's history. Jupiter's gravity reaches out across vast distances. It tugs on asteroids, sometimes capturing them, sometimes flinging them into new orbits. It affects the paths of comets. It may even have prevented a planet from forming in the asteroid belt between Mars and Jupiter, where debris that might have coalesced into a world instead remained fragmented, stirred into chaos by Jupiter's relentless gravitational influence. The planet's equatorial bulge offers another window into its nature. Jupiter rotates once every 9.925 hours, less than 10 hours for a complete rotation. This is the shortest day of any planet in the solar system. To put that in perspective, Earth takes 24 hours to rotate once. Jupiter, despite being 11 times wider, spins more than twice as fast. This rapid rotation creates enormous centrifugal forces, especially at the equator, where material is moving at tremendous speeds relative to the planet's center. The result is that Jupiter bulges outward at the equator and flattens slightly at the poles. It's an oblate spheroid rather than a perfect sphere. The equatorial diameter is 9,276 kilometers longer than the polar diameter. This represents a bulge of roughly 6.5%. If you could see Jupiter as a perfect sphere in your mind and then watched as it began to spin faster and faster, you would see it gradually deform, the middle swelling outward, the top and bottom compressing inward until it reached this oblate configuration. Then, having achieved its current rotation rate, it would maintain that shape indefinitely, or at least for as long as the rotation rate remains constant. Because Jupiter is not a solid body, different parts of it rotate at different speeds. This is called differential rotation, and it's common among gas giants. At Jupiter's equator, the atmosphere completes a rotation in 9 hours, 50 minutes, and 30 seconds. This is called System 1 in the nomenclature astronomers use. At higher latitudes, the rotation takes a bit longer. The polar atmosphere rotates in about 9 hours, 55 minutes, and 41 seconds. That's about 5 minutes slower than the equatorial regions. This might not sound like much, but over time it means that features in the equatorial region lap features at higher latitudes, sliding past them in the same way that runners on the inside lane of a track pull ahead of runners on the outside. The actual rotation rate of Jupiter itself, as opposed to its atmosphere, is measured using the planet's magnetic field, which is generated deep in the interior and therefore rotates with the bulk of the planet. This is called System 3, and it gives a rotation period of 9 hours, 55 minutes, and 29.7 seconds. This is considered Jupiter's true rotation period, the time it takes for the planet as a whole to turn once on its axis. This rapid spin has other consequences beyond the equatorial bulge. It creates powerful winds in the atmosphere, jet streams that race around the planet at different latitudes. These winds can reach speeds of 539 kilometers per hour at the equator. That's faster than the most violent hurricanes Earth has ever produced. And unlike Earth's weather systems, which are driven primarily by solar heating and are constrained by land masses and oceans, Jupiter's jet streams have no continents to slow them down, no oceans to moderate them. They simply blow year after year, century after century, carving the atmosphere into distinct bands. Jupiter's low axial tilt also deserves mention. The planet's axis is tilted only 3.13 degrees relative to its orbital plane. Earth, by comparison, has an axial tilt of 23.5 degrees. This tilt is what gives Earth its seasons. As Earth orbits the Sun, first the northern hemisphere and then the southern hemisphere tilts toward the Sun, creating summer and winter. Jupiter, with its minimal tilt, experiences almost no seasonal variation. The amount of sunlight hitting the northern and southern hemispheres remains essentially constant throughout Jupiter's year. And Jupiter's year is long. It takes the planet 11.86 Earth years to complete one orbit around the Sun. So, while Jupiter spins rapidly, completing a day in less than 10 hours, it moves slowly around its orbit, taking nearly 12 Earth years to return to the same position relative to the Sun and stars. This creates an interesting temporal dynamic. If you could stand on some imaginary platform above Jupiter's clouds, days would flash by with bewildering speed. The Sun would rise and set every 5 hours, though of course you couldn't actually see the Sun clearly through Jupiter's thick atmosphere. But years would drag on, each one containing more than 10,000 Jovian days. The planet orbits at an average distance of 778 million kilometers from the Sun. That's 5.2 astronomical units, where 1 astronomical unit is the average Earth-Sun distance. At this remove, the Sun appears much smaller in Jupiter's sky than it does in ours. The intensity of sunlight is reduced to less than 4% of what Earth receives. This faint sunlight isn't enough to drive Jupiter's weather the way solar heating drives Earth's weather. Instead, Jupiter's atmospheric dynamics are powered primarily by the heat emerging from the planet's interior, that slow contraction, that gentle release of gravitational energy. This internal heat means that Jupiter radiates more energy into space than it absorbs from the Sun. Measurements show that Jupiter emits roughly 1.6 times as much energy as it receives. This might sound like a violation of energy conservation, but it isn't. The extra energy comes from the planet's gradual contraction. As Jupiter shrinks, gravitational potential energy converts to heat. The process is incredibly slow. Jupiter is contracting by about 1 millimeter per year. Over a human lifetime of 80 years, that's 8 centimeters. Over 1,000 years, 1 meter. Over 1,000,000 years, 1 kilometer. These are tiny changes relative to Jupiter's total radius of 69,911 kilometers, but they're sufficient to power the planet's weather systems and maintain its atmospheric temperature at levels far higher than solar heating alone would produce. We've established the basics now. Jupiter is huge, massive, gas-rich, rapidly rotating, and slightly warm from within. It orbits far from the Sun, takes nearly 12 years to complete an orbit, and exhibits virtually no seasons. Its low density and massive size mark it as fundamentally different from the rocky planets of the inner solar system. In the coming sections, we'll build on this foundation, exploring the history of how Jupiter came to be, the structures visible in its atmosphere, and the complex systems that make this planet one of the most dynamic environments we've ever studied. Jupiter is old. Not just old by human standards, where centuries feel like vast spans of time, but old on cosmic scales, ancient in the history of our solar system. The planet formed within the first 1,000,000 years after the Sun itself ignited. This makes Jupiter the oldest planet in the solar system, the first to coalesce from the swirling disk of gas and dust that surrounded the young Sun 4.57 billion years ago. To understand what this means, we need to step back to the beginning. The solar system didn't always exist. 4.6 billion years ago, there was no Sun, no planets, no Earth, no Jupiter. Instead, there was a vast cloud of molecular gas and dust drifting through space in the Orion arm of the Milky Way galaxy. This cloud was cold and dark, held together loosely by its own gravity. Then something happened. Perhaps a nearby supernova exploded, sending shockwaves through the region. Perhaps the cloud simply reached a critical density on its own. Whatever the trigger, the cloud began to collapse. As it collapsed, it began to spin. Conservation of angular momentum ensured this. Just as an ice skater spins faster when pulling in their arms, the collapsing cloud spun faster as it contracted. Over perhaps 100,000 years, it flattened into a rotating disk with a dense, hot core at the center. That core became the Sun. The disk became the birthplace of planets. Within this protoplanetary disk, conditions varied with distance from the young Sun. Close in, temperatures were high enough to vaporize most materials except rock and metal. Farther out, beyond a boundary called the frost line or snow line, temperatures dropped low enough for water and other volatile compounds to condense into ice. The frost line sat at roughly 5 astronomical units from the Sun, right around where Jupiter orbits today. And this is no coincidence. Beyond the frost line, icy planetesimals were abundant. These small bodies, aggregates of ice and rock, had more material to work with than their rocky counterparts in the inner solar system. They grew faster, accumulating mass through collisions and gravitational attraction. In Jupiter's region of the disk, one particular protoplanet hit the jackpot. It grew rapidly, accumulating ice and rock until it reached a mass of approximately 10 to 20 Earth masses. This solid core was massive enough to begin pulling in gas from the surrounding nebula. The gas was primarily hydrogen and helium, the most abundant elements in the disk, leftovers from the primordial material that formed the Sun. Once Jupiter's core reached critical mass, gas accretion accelerated. The planet grew explosively, doubling and redoubling its mass as it pulled in more and more material from the disk. Within less than 1 million years of the solar system's formation, Jupiter had grown to about 20 Earth masses. Most of this was still solid material, ice and rock, but gas was beginning to accumulate on the surface, forming an early atmosphere. For the next few million years, Jupiter continued to grow, but more slowly. It pulled in gas from an ever-widening region, its gravity reaching out to sweep up material that might otherwise have formed other planets or been incorporated into the inner solar system. By 3 to 4 million years after solar system formation, Jupiter had reached roughly 50 Earth masses. At this point, its gravity had become so strong that it opened a gap in the protoplanetary disk, carving out a zone around its orbit where material was either absorbed by Jupiter or expelled to other regions. This gap had profound consequences. It acted as a barrier, preventing material from the outer solar system from migrating inward toward the Sun. It also prevented material from the inner solar system from migrating outward. Meteorite evidence suggests that the solar system had two distinct reservoirs of material during this period, one inside Jupiter's orbit and one outside, and these reservoirs remained separated for millions of years. Jupiter was the gatekeeper, controlling the flow of matter through the solar system. By the time Jupiter finished forming, it had accumulated its current mass of 317.8 Earth masses. Most of this mass came from gas accretion. The final phase of growth was rapid, with the planet reaching its full size in perhaps less than 1,000 years once runaway gas accretion began. This is astonishingly fast on geological timescales. One moment, cosmically speaking, Jupiter was a rocky, icy core with a modest atmosphere. The next moment, it was a gas giant dominating the outer solar system. Jupiter's early growth had cascading effects on the rest of the solar system. Its gravitational influence stirred up the asteroid belt, preventing the material there from coalescing into a planet. It may have caused the migration of other giant planets, Saturn, Uranus, and Neptune, altering their orbits and scattering debris throughout the system. Some models suggest that Jupiter itself migrated inward during its early history, sweeping through the inner solar system and clearing out material before migrating back outward to its current orbit. This is known as the Grand Tack hypothesis, and while it remains debated, it offers an explanation for several puzzling features of the solar system's architecture. One of those features is the small size of Mars. If Jupiter hadn't interfered, Mars might have grown much larger, potentially becoming a planet comparable to Earth. But Jupiter's gravity prevented material from accumulating in Mars's region, limiting the red planet to roughly 10% of Earth's mass. Another consequence may be the absence of super-Earths in our solar system. Many exoplanetary systems discovered around other stars contain planets with masses between Earth and Neptune, orbiting close to their parent stars. Our solar system lacks such planets. Jupiter's early presence may have prevented them from forming or caused them to be ejected from the system before they could establish stable orbits. In a very real sense, Jupiter shaped the solar system we inhabit. Its massive gravitational influence determined which planets could form, where they could form, and how large they could grow. Without Jupiter, Earth might not exist, or it might exist in a very different form. The asteroid belt might be a planet. Mars might be much larger. The outer solar system might contain several additional ice giants. The entire architecture of our cosmic neighborhood depends in part on the fact that Jupiter formed first, grew rapidly, and established itself as the gravitational anchor of the outer solar system. Understanding Jupiter's age required clever detective work. Scientists can't bring back samples from Jupiter the way they can from the Moon or Mars. Instead, they studied meteorites, fragments of asteroids that fall to Earth. By analyzing isotopes of tungsten and molybdenum in these meteorites, researchers were able to determine that they came from two distinct populations, one that formed inside Jupiter's orbit and one that formed outside. The key finding was that these two populations remained separated for several million years, from about 1 million years to 3 or 4 million years after the solar system's birth. The only plausible explanation for this separation is that Jupiter formed during this period and created a barrier preventing mixing. By dating the meteorites themselves, scientists could bracket Jupiter's formation timeline. The results showed that Jupiter's core must have formed within the first million years, making it the oldest planet. This finding, published in 2017, represented a major breakthrough in our understanding of solar system history. At the time the solar nebula was dispersing, roughly 4 to 10 million years after the Sun's formation, Jupiter was already a massive presence. The nebula was the disk of gas from which all the planets formed. Once it dispersed, blown away by intense solar radiation and winds from the young Sun, no more gas was available for planet formation. The fact that Jupiter and Saturn are gas giants means they must have formed before this dispersal. The fact that Uranus and Neptune are smaller and have less hydrogen and helium suggests they formed later after much of the gas was already gone. Jupiter's early formation also affected its composition. Because it formed so quickly while the nebula was still rich in gas, Jupiter was able to accrete material that closely matched the composition of the original solar nebula, which in turn matched the composition of the Sun. That's why Jupiter's atmosphere is roughly 76% hydrogen and 24% helium by mass, very similar to the Sun's 71% hydrogen and 28% helium. The small difference in helium abundance is due to helium precipitation within Jupiter. Deep in the planet's interior, helium droplets form and rain downward toward the core, gradually depleting the upper atmosphere of helium while enriching the deeper layers. In its youth, Jupiter was even more impressive than it is today. Recent research suggests that when the solar nebula dispersed, Jupiter was approximately twice its current diameter. It was hotter, glowing with the heat of its rapid formation and contraction. Its magnetic field was stronger than it is now, perhaps 3 to 10 times stronger. Over billions of years, as Jupiter gradually cooled and contracted, it shrank to its present size. But that contraction is still ongoing. That millimeter per year, that slow release of gravitational energy that keeps Jupiter warmer than it has any right to be at its distance from the Sun. Jupiter spins. It spins faster than any other planet in the solar system. One complete rotation takes 9 hours, 55 minutes, and 29.7 seconds. This is less than half the time it takes Earth to rotate once. Despite being 11 times wider than Earth, Jupiter completes a day in less than 10 hours. This rapid rotation is one of Jupiter's defining characteristics. It affects nearly every aspect of the planet's appearance and behavior. It shapes the atmosphere into bands. It generates the magnetic field. It creates the equatorial bulge. It drives winds that howl at speeds no terrestrial hurricane could match. To understand Jupiter, you must first understand its spin. Imagine you're watching Jupiter from a fixed point in space, somewhere above its north pole. The planet rotates counterclockwise from this perspective, the same direction Earth rotates. But where Earth's rotation is stately and measured, taking 24 hours to complete, Jupiter whips around with astonishing speed. The equator moves at roughly 12.6 kilometers per second, That's 45,360 kilometers per hour. This tremendous velocity creates a centrifugal force that flings material outward, causing the equator to bulge. The bulge is substantial. Jupiter's equatorial radius is 71,492 kilometers, while its polar radius is only 66,854 kilometers. The difference is 4,638 kilometers. To put that in perspective, that's more than 1/3 of Earth's diameter. If you could somehow slice Jupiter in half, vertically, from pole to pole, you would see that it's distinctly elliptical, noticeably wider at the middle, than at the top and bottom. This oblateness affects Jupiter's gravitational field. The planet isn't a perfect sphere, so its gravity isn't perfectly symmetrical. Spacecraft passing near Jupiter experience subtle tugs and pulls that reveal the planet's internal structure. By carefully measuring these gravitational variations, scientists can learn about the distribution of mass within Jupiter, which, in turn, tells us about the density of different layers, the size of the core, and the depth to which various atmospheric features extend. The rapid rotation also creates a strong Coriolis effect. On Earth, the Coriolis effect causes moving objects to curve to the right in the northern hemisphere and to the left in the southern hemisphere. It's why hurricanes spin counterclockwise in the north and clockwise in the south. On Jupiter, the Coriolis effect is even more pronounced because of the faster rotation. This helps organize the atmosphere into distinct bands parallel to the equator, with winds blowing eastward in some bands and westward in others. These bands are one of Jupiter's most striking visual features, visible even through small telescopes. The lighter bands are called zones, and the darker bands are called belts. Zones are regions of upwelling, where gas rises from deeper in the atmosphere, bringing fresh ammonia and other compounds to high altitude where they condense into bright white clouds. Belts are regions of downwelling, where gas sinks back down, allowing us to see into deeper, darker cloud layers. The boundaries between zones and belts are turbulent. Strong winds blow along these boundaries, and the interaction between adjacent jet streams creates eddies and vortices. Some of these vortices are small and short-lived. Others, like the Great Red Spot, can persist for centuries. The differential rotation of Jupiter's atmosphere means that these features don't remain in fixed positions relative to the planet as a whole. They drift in longitude slowly, moving around the planet, though they generally stay at constant latitudes. At the equator, the atmosphere rotates faster than at higher latitudes. System 1, the equatorial rotation system, has a period of 9 hours, 50 minutes, and 30 seconds. System 2, which applies to latitudes above about 10 degrees north and south, has a period of 9 hours, 55 minutes, and 41 seconds. That's about 5 minutes slower. This difference might seem small, but it means that over the course of a Jupiter year, which lasts nearly 12 Earth years, the equatorial regions complete about 60 more rotations than the mid-latitude regions. This differential rotation is possible because Jupiter has no solid surface. On Earth, the atmosphere rotates at roughly the same speed as the surface beneath it, give or take some variation due to winds. But Jupiter has no surface to couple to. The visible clouds we see are just the top layer of an atmosphere that extends downward for thousands of kilometers, gradually transitioning into liquid and then into exotic states of matter we can barely imagine. Different layers can rotate at different speeds without grinding against anything solid. Deeper in the planet, perhaps halfway to the center, pressure and temperature become so extreme that hydrogen is crushed into a metallic state. In this region, electrons are stripped from hydrogen atoms, and the resulting fluid conducts electricity. This metallic hydrogen layer is thought to rotate approximately with the planet as a whole at the System 3 rate of 9 hours, 55 minutes, and 29.7 seconds. This is the rotation period determined by observing Jupiter's magnetic field, which is generated in the metallic hydrogen layer and therefore rotates with it. The magnetic field itself is one of the consequences of Jupiter's rapid rotation. Deep within the planet, the metallic hydrogen layer acts like a dynamo. As it rotates, convection currents within the fluid carry electric charge, and these moving charges generate a magnetic field. This is the same mechanism that generates Earth's magnetic field, except on Jupiter, the effect is magnified by the planet's size and rotation rate. Jupiter's magnetic field is the strongest of any planet in the solar system, excluding the Sun. At the cloud tops, the field strength is about 4.3 Gauss, compared to Earth's half a Gauss. But because Jupiter is so much larger than Earth, the total extent of its magnetosphere is enormous. The magnetosphere is the region of space dominated by a planet's magnetic field, where the field is strong enough to deflect the solar wind and trap charged particles. Jupiter's magnetosphere extends outward to a distance of about 7 million kilometers on the side facing the Sun and stretches all the way to Saturn's orbit on the opposite side. It is the largest structure in the solar system, aside from the Sun's own heliosphere. Within this magnetosphere, charged particles spiral along magnetic field lines, creating intense radiation belts. These belts are far more dangerous than Earth's Van Allen belts. The radiation environment near Jupiter is so harsh that spacecraft must be carefully shielded to survive even brief passages through the inner magnetosphere. If humans ever attempt to send astronauts to Jupiter's moons, they will need to contend with radiation doses that would be lethal within hours. The rapid rotation also affects Jupiter's interior structure. Centrifugal force from the spin partially offsets gravity, especially near the equator. This means that material at Jupiter's equator is under slightly less pressure than material at the same depth near the poles. Over time, this can lead to variations in composition and structure between equatorial and polar regions. However, because Jupiter is fluid throughout, convection constantly mixes the interior, preventing large-scale stratification from developing. 1. Might wonder whether Jupiter's rotation is slowing down. Earth's rotation is gradually slowing due to tidal interactions with the Moon. Each year, Earth's day lengthens by about 2 milliseconds as the Moon's gravity creates tidal bulges in Earth's oceans, and friction between the oceans and the seafloor dissipates rotational energy. Jupiter also experiences tidal interactions, primarily with its large moons, especially Io. However, Jupiter is so much more massive than its moons that the effect is negligible. Jupiter's rotation period has remained essentially constant over the time we've been observing it, and models suggest it has been stable for billions of years. The spin of Jupiter creates a rhythm, a periodicity that governs many of the planet's phenomena. The magnetic field wobbles as it rotates, creating oscillations in the radio emissions that Jupiter produces. These emissions were first detected in the 1950s, and it was through studying their periodicity that astronomers were able to determine Jupiter's rotation rate before spacecraft could measure it directly. The auroras at Jupiter's poles brighten and dim with the rotation period as different parts of the magnetosphere swing into view. Even the temperature distribution in Jupiter's atmosphere shows some correlation with the rotation. The poles are slightly cooler than the equator, in part because they receive less direct sunlight, but also because the rapid rotation drives heat transport from the equator toward higher latitudes, creating a more uniform temperature distribution than would exist on a non-rotating planet. All of this from a simple fact. Jupiter spins fast. Less than 10 hours for a complete rotation. This one characteristic ripples through the entire planet, shaping its form, driving its weather, generating its magnetic field, creating its radiation belts, organizing its clouds into bands, and maintaining a dynamic equilibrium that has persisted for billions of years. When you look at Jupiter through a telescope and see those bands, those swirls, that restless atmosphere, you're seeing the visible manifestation of a planet spinning faster than any other world we know. Jupiter's atmosphere is a thing of beauty and complexity. When you observe the planet through a telescope, you're immediately struck by the bands that circle it, parallel to the equator. These aren't static markings painted on a solid surface. They're dynamic features created by atmospheric circulation, jet streams that encircle the planet at different latitudes, zones where gas rises, and belts where it falls. The atmosphere we can see extends down to a pressure of about 1 bar, which is roughly equivalent to atmospheric pressure at sea level on Earth. This visible layer is perhaps 100 kilometers thick, maybe less, depending on where you measure. Below this lies a vast expanse of atmosphere extending downward for thousands of kilometers, becoming progressively denser and hotter as pressure mounts. At the visible cloud tops, temperatures hover around -110 degrees Celsius. This is cold enough to freeze ammonia, and indeed the white clouds that give the zones their bright appearance are composed primarily of ammonia ice crystals. These clouds form at high altitude when rising gas cools and the ammonia condenses. The process is similar to the formation of water vapor clouds on Earth, except the condensing material is ammonia instead of water. Deeper in the atmosphere, below the ammonia clouds, lies a layer where conditions allow ammonium hydrosulfide to condense. This compound forms when ammonia reacts with hydrogen sulfide. Ammonium hydrosulfide clouds are darker and redder than ammonia clouds, and in regions where downwelling has removed the upper ammonia layer, we can see through to these deeper clouds. This is what gives the belts their brown and tan coloration. We're seeing into a deeper layer of the atmosphere, glimpsing cloud decks that exist tens of kilometers below the ammonia ice layer. Even deeper, perhaps 150 kilometers below the visible cloud tops, temperatures rise high enough for water to exist in liquid form. At these depths, pressure might be 5 to 10 times Earth's atmospheric pressure, and temperatures could be around 0 degrees Celsius or higher. Water clouds may form here, though we can't see them directly through the upper layers. Everything we know about this deep water cloud layer comes from indirect evidence, computer models of atmospheric circulation, and thermodynamic calculations. The vertical structure of Jupiter's atmosphere creates a complex environment. Temperature generally increases with depth, as you'd expect on a planet that's radiating internal heat. But the increase isn't uniform. There are regions where temperature actually decreases with depth, at least temporarily. These temperature inversions can trap gases and create stable layers that resist mixing. The jet streams that organize the atmosphere into bands are among the most powerful winds in the solar system. At the equator, eastward winds blow at speeds exceeding 539 kilometers per hour. These are not occasional gusts, but sustained winds that have persisted for as long as we've been able to measure them. At higher latitudes, the winds alternate direction. Some bands blow eastward, others westward, creating a striped pattern of alternating circulation. The boundaries between these jet streams are violent places. Where eastward and westward winds meet, enormous wind shear develops. This shear creates turbulence and spawns the eddies and vortices that populate Jupiter's atmosphere. The Great Red Spot, which we'll discuss in detail later, is one such vortex, formed and sustained by the interaction between opposing jet streams. The zones, those bright bands where gas rises, are generally cooler at the cloud tops than the belts. This seems counterintuitive until you remember that the gas in the zones is rising. It's coming from warmer depths, but as it rises, it expands and cools. By the time it reaches the altitude where ammonia condenses, it's cold enough to form bright, reflective clouds. The belts, where gas sinks, are warmer at the cloud tops. The descending gas compresses and heats as it sinks, and this heating can evaporate clouds, creating the clear, cloud-free regions that allow us to see into the darker depths. Jupiter's atmosphere is about 90% hydrogen and 10% helium by number of molecules. These percentages translate to roughly 75% hydrogen and 24% helium by mass, very close to the composition of the Sun and of the original solar nebula from which Jupiter formed. The remaining 1% includes a variety of compounds: methane, ammonia, water vapor, hydrogen sulfide, neon, argon, and traces of many other elements and molecules. Some of these trace compounds play outsized roles in creating the colors we see. Ammonia gives the white zones their bright appearance. But what creates the reds, oranges, and browns of the belts? This is one of Jupiter's enduring mysteries. The leading candidates include complex organic molecules created by photochemistry in the upper atmosphere, phosphorus compounds brought up from deeper layers, or sulfur compounds in various oxidation states. Laboratory experiments have shown that when you expose mixtures of ammonia, methane, and other Jovian gases to ultraviolet light or electrical discharges, you get complex organic molecules called tholins. These tholins are reddish-brown and could account for some of the coloration we see. But the exact chemistry is still uncertain, partly because we don't know the precise composition of Jupiter's atmosphere at all depths, and partly because the relevant chemical reactions are complex and not fully understood. The vertical mixing in Jupiter's atmosphere is vigorous. Convection carries material from deep layers up to the visible cloud tops and then back down again in a continuous cycle. This mixing happens on timescales of days to weeks for individual parcels of gas. It means that material from thousands of kilometers deep can potentially reach the cloud tops, providing a window into the composition of Jupiter's interior. One of the surprises from the Galileo probe, which descended into Jupiter's atmosphere in December of 1995, was that the atmosphere at the entry site was unusually dry. The probe found less water than expected, about 1/10 the solar abundance. This was puzzling because models predicted that Jupiter should have several times the solar abundance of oxygen locked up in water. The best explanation is that the probe happened to enter in a dry region, possibly analogous to a desert on Earth. Other parts of Jupiter's atmosphere are likely much wetter, with water vapor concentrations matching or exceeding solar abundances. The Galileo probe also measured wind speeds directly as it descended. It found that winds increased with depth, remaining strong even 60 kilometers below the cloud tops, where pressure exceeded 20 bars. This was surprising. Many scientists expected winds to die out quickly with depth. Instead, the jet streams appear to extend deep into the atmosphere, perhaps hundreds of kilometers down, until pressure becomes high enough for friction to dissipate the wind energy. Temperature measurements from the probe showed the atmosphere warming with depth at a rate close to the adiabatic lapse rate. This is the rate at which temperature increases when you compress a gas without adding or removing heat, and it's exactly what you'd expect in a well-mixed atmosphere undergoing convection. The atmosphere wasn't stratified, but rather churning and turning over, convecting heat from the interior upward towards space. Jupiter's visible cloud features are ephemeral on human timescales, but stable on Jovian timescales. Small features, white ovals and brown barges and festoons, can form and dissipate within weeks or months. Medium-sized features may last years or decades. The largest features, like the Great Red Spot, persist for centuries. This range of timescales reflects the range of energies involved. Small features are easily disrupted by turbulence. Large features have enough energy and momentum to resist disruption, shearing smaller vortices apart rather than being disrupted by them. The belts and zones themselves shift position occasionally, usually by small amounts. Every few years, a belt might fade, becoming lighter and harder to distinguish from adjacent zones. Then, months or years later, it might darken again as circulation patterns change and clouds clear. The mechanisms driving these changes are not fully understood. They likely involve shifts in the convective patterns that drive upwelling and downwelling, perhaps triggered by changes in the temperature gradient or by the accumulation or dissipation of certain chemicals. One particularly dramatic event is the South Equatorial Belt fade. Every decade or two, the South Equatorial Belt, normally one of the most prominent dark features on Jupiter, fades to a pale tan or even white. It can remain faded for months or even a year or more. Then, often suddenly, a dark spot appears somewhere along the belt, and the darkness spreads outward from this point until the entire belt has returned to its normal appearance. The trigger for the fade and the subsequent revival remains unclear, though it almost certainly involves changes in the vertical structure of the atmosphere and the cloud layers. Higher in Jupiter's atmosphere, above the ammonia clouds, lies the stratosphere. Here, temperature increases with altitude, the opposite of what happens in the troposphere below. The stratosphere is heated by the absorption of ultraviolet sunlight and by infrared radiation from deeper layers. It's a thin, tenuous region compared to the dense troposphere below, but it's important for atmospheric chemistry. Photochemical reactions in the stratosphere create complex hydrocarbons and other molecules that can eventually settle downward into the troposphere. Even higher lies the thermosphere, where temperatures can reach 1000 degrees Celsius or more despite the tenuous atmosphere. This heating is driven by interactions between the upper atmosphere and the magnetosphere, by auroral processes we'll discuss later, and by the absorption of high-energy solar radiation. The thermosphere is so tenuous that it barely qualifies as atmosphere in the conventional sense. Density is extremely low, and particles can travel long distances without colliding. At the very top of the atmosphere is the exosphere, where atmospheric particles can escape into space if they achieve sufficient velocity. Jupiter's strong gravity makes escape difficult, so very little material is lost this way. The exosphere blends gradually into the surrounding space environment with no sharp boundary between atmosphere and vacuum. This multi-layered structure, from the deep water clouds to the hot thermosphere, creates an atmospheric environment unlike anything on Earth. It's a place of perpetual motion, of winds that never cease, of clouds that condense and evaporate in endless cycles, of jet streams that have flowed for billions of years. And woven through this atmosphere, like eddies in a stream, are the vortices and storms, the ovals and festoons, and, most famously, the Great Red Spot. The Great Red Spot is Jupiter's most famous feature. It's a storm, an anticyclonic vortex, a massive high-pressure region where winds spiral counterclockwise in Jupiter's southern hemisphere. It's large enough to swallow Earth. It's persisted for at least 190 years, and quite possibly much longer. It's a shade of brick red to salmon pink, depending on when you observe it, and it stands out against the surrounding cloud, belts like a jewel set into the atmosphere. The spot rotates counterclockwise, completing one rotation approximately every 6 days. This might not sound fast, but remember that the spot is huge. Its current size is roughly 16,000 kilometers east to west and 10,500 kilometers north to south. That means the winds at its edge are traveling around the perimeter at speeds approaching 430 kilometers per hour. These aren't winds in the center of the storm, which may be relatively calm, but rather at the boundary where the spot's circulation interacts with the surrounding atmosphere. The Great Red Spot has been under observation since at least 1831, when amateur astronomer Samuel Heinrich Schwabe sketched it. The sketch clearly shows an oval structure in the correct latitude, and subsequent observations through the 1800s consistently noted its presence. However, there are earlier observations that might also depict the spot. In 1665, Giovanni Cassini described a permanent spot on Jupiter. Some historians believe this was the Great Red Spot, which would make it at least 360 years old. Others think Cassini observed a different, temporary feature. We simply don't know for certain how long the spot has existed, but a conservative estimate puts its age at nearly 200 years, and it may be considerably older. Over the time we've been observing it, the Great Red Spot has changed. In the late 1800s, it was much larger than it is today, stretching perhaps 41,000 kilometers across at its widest point. That's more than 3 times Earth's diameter. It was also more elongated, with a length-to-width ratio of about 2 to 1. Throughout the 20th century, the spot gradually shrank. By the 1970s, when the Voyager spacecraft made their flybys, it was about 23,000 kilometers across. By the time the Juno spacecraft arrived in 2016, it had shrunk further to about 16,000 kilometers. The shrinking continues today. Recent observations suggest the spot is contracting at a rate of roughly 930 kilometers per year. If this rate continues, the spot might become circular within a few decades. However, predicting the spot's future is difficult. It might stabilize at a smaller size, it might even re-expand if circulation patterns change, or it might eventually dissipate entirely. Though, given its longevity, this seems unlikely in the near term. The color of the Great Red Spot also varies. Sometimes it appears a deep brick red. Other times, it fades to a pale salmon pink or even light tan. The color changes seem to correlate with changes in size and shape, though the exact mechanism isn't clear. The prevailing theory is that the color comes from complex organic molecules, tholins, created by photochemistry in the upper atmosphere. When the spot is particularly vigorous, it may dredge up material from deeper layers, or it may expose more of its interior to sunlight, leading to enhanced tholin production and a darker color. The Great Red Spot sits at about 22 degrees south latitude, nestled between 2 westward flowing jet streams. This location is crucial to its stability. The jet streams to the north and south shear past the spot in opposite directions, and these opposing flows help to confine the spot and prevent it from drifting too far in latitude. The spot does drift in longitude, slowly moving westward relative to System 2 rotation at a rate that varies from year to year. Sometimes it drifts quickly, sometimes slowly, but it always remains at approximately the same latitude. What powers the Great Red Spot? Why has it persisted for so long when Earth's hurricanes dissipate in days or weeks? The answer lies in the energy source. Earth's hurricanes are driven by warm ocean water. Once they move over land or cooler water, they lose their energy source and decay. The Great Red Spot, by contrast, is driven by internal heat from Jupiter's interior and by energy extracted from the jet streams that surround it. As long as Jupiter continues to radiate heat and the jet streams continue to flow, the spot has a continuous energy supply. The spot's depth has been a long-standing question. Is it a shallow feature, confined to the upper atmosphere, or does it extend deep into Jupiter? Recent data from the Juno spacecraft suggests the spot extends at least 300 kilometers below the cloud tops. That's much deeper than expected. At those depths, pressure is tens of times higher than at the surface, and temperature is significantly warmer. The fact that the spot extends so deep implies it's tapping into substantial energy reserves in the lower atmosphere. Interactions between the Great Red Spot and other atmospheric features are common. Smaller storms occasionally approach the spot and are either absorbed or flung away. White ovals, smaller anticyclonic storms similar to the Great Red Spot, but much smaller and paler, have merged with the spot or passed close to it on numerous occasions. In 2008, a smaller storm called Oval BA, nicknamed Red Spot Jr., passed close to the Great Red Spot. The two storms influenced each other gravitationally, their circulations interacting, but they didn't merge. They simply swung past each other and continued on their separate paths. The interior of the Great Red Spot is thought to be relatively calm, much like the eye of a hurricane on Earth. The most intense winds are at the outer edge, where the spot's rotation shears against the surrounding atmosphere. Moving inward from the edge, wind speeds decrease, though measurements of this are difficult because we can't place instruments inside the spot. Everything we know comes from remote sensing, from tracking cloud features in images and using spectroscopy to measure wind speeds via the Doppler shift. Temperature measurements show that the Great Red Spot is colder at its cloud tops than the surrounding atmosphere. This is consistent with an anticyclonic high-pressure system. In such systems, gas is descending in the center, and as it descends, it compresses and warms. But the warming is happening at depth. At the cloud tops, the descending gas has displaced the upper atmosphere, pushing it aside, and the result is a cooler upper region. The temperature difference is only a few degrees, but it's measurable with infrared instruments. The Great Red Spot also shows vertical structure. High-resolution images reveal complex swirls and filaments within the spot, suggesting that it's not a simple, homogeneous vortex, but rather a complex system with multiple circulation cells and possibly multiple layers rotating at different speeds. Some researchers have proposed that the spot consists of a shallow upper layer, extending perhaps 50 to 100 kilometers deep, and a deeper layer extending several hundred kilometers. The two layers might rotate at different rates, though. They're coupled together by friction and viscosity. One of the persistent mysteries is why the Great Red Spot is red. We know that fresh white ammonia clouds are common in Jupiter's atmosphere, and if the spot was simply bringing up fresh ammonia, it should be white. The fact that it's red suggests that something in the spot is creating or concentrating colored compounds. Photochemistry is the leading candidate. Ultraviolet light from the sun can break apart ammonia and methane molecules, and the fragments can recombine into complex organic molecules that are reddish-brown. Laboratory experiments support this. When researchers expose mixtures of ammonia, methane, and other gases to UV light, they produce reddish tholins. However, The spot's interior should be somewhat shielded from direct sunlight by the ammonia clouds above it. One possibility is that the spot's vigorous circulation brings material up from deeper layers, where it's exposed to sunlight at the edges of the storm, and then the colored compounds are mixed back into the spot's interior. Another theory involves phosphorus. Jupiter's interior contains phosphorus, and convective currents could bring phosphorus compounds up from depth. Certain phosphorus allotropes are red, and they might contribute to the spot's color. However, the concentration of phosphorus needed would be quite high, and it's not clear that convection could transport enough phosphorus to the visible cloud layers to account for the coloration. The Great Red Spot is not unique in being a long-lived atmospheric feature. Jupiter hosts several other persistent ovals, though none as large or as famous. Oval Ba, mentioned earlier, formed in 2000 from the merger of three smaller white ovals that had existed since the 1930s. After the merger, Oval Ba gradually turned red, becoming a smaller sibling to the Great Red Spot. Why it turned red after being white for decades is another mystery, possibly related to a change in circulation that brought more material up from depth or altered the exposure to sunlight. Studying the Great Red Spot provides insights into atmospheric dynamics not just on Jupiter, but on other planets as well. Neptune has a similar feature, the Great Dark Spot, though Neptune's spot appears and disappears on timescales of years rather than centuries. Saturn occasionally develops large storms, though they don't persist as long as Jupiter's. Understanding why Jupiter can sustain such long-lived vortices helps us understand the conditions necessary for atmospheric stability and the mechanisms that allow energy to be stored and released in planetary atmospheres. The Great Red Spot is also a reminder of the dynamism of Jupiter's atmosphere. Despite being a gas giant with no solid surface, Jupiter is far from a featureless ball of gas. Its atmosphere churns and swirls, creating structures that dwarf continents on Earth, storms that outlast civilizations. The spot has been spinning in Jupiter's atmosphere since before the American Civil War, perhaps since before the United States existed as a nation. It will likely continue spinning long after we're gone, a testament to the power and persistence of planetary-scale weather systems. Jupiter doesn't travel through space alone. It's accompanied by a retinue of at least 95 known moons and probably many more small ones yet to be discovered. But among this multitude, 4 stand out. These are the Galilean moons, discovered by Galileo Galilei in January of 1610 when he turned his newly built telescope toward Jupiter. They're named Io, Europa, Ganymede, and Callisto, and each is a world unto itself. Io is the innermost of the 4. It orbits Jupiter at a distance of 421,700 kilometers, completing one orbit every 1.77 days. This proximity to Jupiter subjects Io to tremendous tidal forces. Jupiter's gravity pulls on Io, stretching and squeezing it as the moon orbits. The result is the most volcanically active body in the solar system. Io's surface is young, constantly resurfaced by volcanic eruptions. There are no impact craters on Io, which is unusual. Almost every other solid body in the solar system is covered with impact craters, the scars of billions of years of bombardment. But on Io, volcanic activity erases craters as quickly as they form. The surface is dominated by volcanic features, calderas, lava flows, volcanic mountains, plumes of sulfur and sulfur dioxide erupting hundreds of kilometers above the surface. When Voyager 1 flew past Io in 1979, it captured images of 9 active volcanic eruptions occurring simultaneously. This was the first time active volcanism had been observed anywhere other than Earth. Since then, every spacecraft that has observed Io has seen active eruptions. The volcanic plumes are spectacular. Some reach altitudes of 300 kilometers, towering above Io's surface. The material in these plumes doesn't fall back immediately because Io's gravity is weak, only 18% of Earth's. Instead, sulfur and sulfur dioxide particles arc gracefully back to the surface, sometimes landing hundreds of kilometers from the vent. The heat output from Io is staggering. The Moon radiates roughly 2.5 watts per square meter, averaged over its entire surface. That might not sound like much, but integrated over Io's entire surface area, it's about 100 trillion watts. That's about twice the heat output of all of Earth's volcanoes combined. This heat comes from tidal heating, from the constant flexing of Io's interior as it orbits Jupiter. Io's surface is a patchwork of colors: yellow, orange, red, white, black. The colors come from sulfur and sulfur compounds in various forms. Sulfur can be yellow, orange, or red, depending on temperature and molecular structure. Black regions are likely silicate lava flows, similar to basaltic lava on Earth. White regions are probably sulfur dioxide frost. The overall effect is unlike anywhere else in the solar system, a landscape that looks almost painted, alien, and surreal. Europa, the next moon outward, is Io's opposite in many ways. Where Io is volcanic and hellish, Europa is icy and serene. Europa orbits at 671,000 kilometers from Jupiter, completing one orbit every 3.55 days. Its surface is one of the smoothest in the solar system, covered with water ice that reflects sunlight brilliantly. Europa's surface is young, though not as young as Io's. There are relatively few impact craters, suggesting that the surface has been resurfaced geologically recently, perhaps within the last 100 million years. The surface is crisscrossed with cracks and ridges, dark lines that stretch for thousands of kilometers. These features are thought to result from tidal flexing, similar to what happens on Io but less extreme. The ice shell cracks and shifts, and liquid water or slush from below wells up into the cracks, freezing and creating new surface features. Beneath Europa's icy crust lies what many scientists believe is a global ocean of liquid water. The evidence for this ocean is compelling. Europa's magnetic field behaves in a way that suggests a conducting layer beneath the surface, and salty water is a good conductor. The Moon's surface features, the cracks and ridges, are consistent with a floating ice shell overlying liquid. And tidal heating from Jupiter provides enough energy to keep water liquid despite Europa's great distance from the Sun. The ocean, if it exists, might be 100 kilometers deep. The ice crust floating on top might be 15 to 25 kilometers thick, though this is uncertain. Beneath the ice, in the dark, pressurized ocean, conditions might be suitable for life. This is speculative, of course. We have no direct evidence of life on Europa, but the ocean would have liquid water, a source of energy in the form of tidal heating and potentially chemical nutrients leached from Europa's rocky interior. These are the ingredients that, on Earth, have proven sufficient for life to arise. Plumes of water vapor have been tentatively detected erupting from Europa's surface, possibly from cracks in the ice where the ocean below is exposed. If these plumes are real, they offer a tantalizing possibility for future missions. A spacecraft could fly through a plume and analyze the material, providing a sample of Europa's ocean without having to drill through kilometers of ice. The Clipper spacecraft, currently en route to Jupiter, is designed to investigate Europa in detail, mapping its surface, analyzing its composition, and searching for active plumes. Ganymede is the third Galilean moon and the largest moon in the solar system. Its diameter is 5,268 kilometers, larger than the planet Mercury. Ganymede orbits at 1,070,000 kilometers from Jupiter, taking 7.15 days to complete one orbit. Ganymede is unique among moons in having its own magnetic field, generated by a liquid iron core deep within the moon. This magnetic field interacts with Jupiter's magnetosphere, creating a small magnetosphere around Ganymede itself. Ganymede's surface is divided into two main types of terrain: dark, heavily cratered regions that are billions of years old, and lighter, grooved terrain that appears younger. The grooved terrain consists of parallel ridges and valleys, possibly formed by tectonic activity. The dichotomy between old and young terrain suggests that Ganymede was geologically active in the past, perhaps driven by tidal heating, though it appears to be less active today than Io or Europa. Like Europa, Ganymede may harbor a subsurface ocean. Measurements of its magnetic field and gravitational field suggest that beneath a thick ice crust, perhaps 150 kilometers thick, there could be a layer of liquid water. This ocean would be buried far deeper than Europa's, making it less accessible, but it might still exist, kept liquid by tidal heating and heat from radioactive decay in Ganymede's core. Ganymede's thin atmosphere consists mostly of oxygen. This isn't breathable oxygen, though, and the atmosphere is so tenuous it barely qualifies. It's created when charged particles from Jupiter's magnetosphere strike the ice on Ganymede's surface, breaking water molecules apart. The hydrogen escapes into space, being light, while the heavier oxygen lingers, forming a thin exosphere. The surface pressure is only about 1/10,000,000th of Earth's atmospheric pressure. Callisto is the outermost Galilean moon, orbiting at 1,883,000 kilometers from Jupiter. Its orbital period is 16.69 days. Callisto is almost as large as Ganymede, with a diameter of 4,821 kilometers. Unlike the other Galilean moons, Callisto shows little sign of geological activity. Its surface is ancient, heavily cratered, saturated with impacts that have accumulated over billions of years. Callisto's surface is dark, reflecting only about 20% of the sunlight that hits it. This low reflectivity, or albedo, is due to the presence of dark material, possibly carbonaceous or rocky, mixed with the ice. The most prominent feature on Callisto is Valhalla, a multi-ring impact basin 4,000 kilometers across. Valhalla consists of a bright central region surrounded by concentric rings of ridges. It's one of the largest impact structures in the solar system, formed when a large asteroid or comet struck Callisto billions of years ago. Despite its ancient surface, Callisto may also have a subsurface ocean. Magnetic field measurements suggest a conducting layer beneath the surface, consistent with a salty ocean at depth. If Callisto does have an ocean, it would be buried beneath a thick ice crust perhaps 200 kilometers deep, even more inaccessible than Ganymede's. The ocean would be kept liquid by heat from radioactive decay, as Callisto is far enough from Jupiter that tidal heating is minimal. The 4 Galilean moons are locked in an orbital resonance called the Laplace resonance. For every 4 orbits Io completes, Europa completes exactly 2, and Ganymede completes exactly 1. This resonance ensures that the moons periodically align in the same configuration, and the gravitational interactions between them maintain the eccentricities of their orbits. These eccentric orbits are what cause the tidal heating on Io and Europa. If the orbits were perfectly circular, there would be no variation in tidal stress, and much less heating. The resonance keeps the orbits slightly eccentric, ensuring continued tidal flexing and geological activity. The Galilean moons are large enough that each would be considered a significant planet if they orbited the Sun instead of Jupiter. Ganymede and Callisto are larger than Mercury. Io and Europa are comparable in size to Earth's moon. Each has its own geology, its own history, its own mysteries. Together, they form a miniature solar system around Jupiter, a laboratory for studying planetary processes in a range of environments. Future missions to the Jupiter system will focus heavily on these moons. Europa Clipper will study Europa's ocean and surface. The European Space Agency's JUICE mission, also en route, will study Ganymede, Callisto, and Europa. There's even talk of a mission to Io, though the intense radiation near Jupiter makes such a mission challenging. Each mission will add to our understanding, revealing new details about these fascinating worlds. For now, though, they remain distant enigmas, visible from Earth as tiny points of light accompanying Jupiter. Galileo saw them as such in 1610, and his observation fundamentally changed our understanding of the cosmos. Before Galileo, it was believed that everything orbited Earth. The discovery that moons orbited Jupiter proved that not everything in the heavens revolved around our planet. It was evidence for the Copernican model, in which Earth and the other planets orbit the Sun. The Galilean moons were instrumental in overturning the geocentric view of the universe and ushering in the modern era of astronomy. Jupiter's magnetic field is a colossus. It extends millions of kilometers into space, dwarfing the planet itself. If you could somehow see magnetic field lines, if they glowed or shimmered in visible light, Jupiter's magnetosphere would be one of the largest and brightest objects in the night sky, visible to the naked eye from Earth despite the immense distance. The magnetosphere is the region of space dominated by Jupiter's magnetic field. On the side facing the Sun, the magnetosphere is compressed by the solar wind, a stream of charged particles flowing outward from the Sun. On the opposite side, the magnetosphere stretches outward into a long tail that can extend all the way to Saturn's orbit, a distance of roughly 650 million kilometers from Jupiter. This magnetotail is dynamic, constantly buffeted by variations in the solar wind, sometimes snapping and reconnecting in events that release enormous amounts of energy. The strength of Jupiter's magnetic field at the cloud tops is about 4.3 Gauss. This is roughly 10 times stronger than Earth's magnetic field at Earth's surface. But because Jupiter is so much larger than Earth, the total magnetic moment, a measure of the field's overall strength, is about 20,000 times greater than Earth's. This immense field is generated deep within Jupiter by the motion of metallic hydrogen in the planet's interior. The metallic hydrogen layer begins at about 7,000 kilometers below the cloud tops. At that depth, the pressure becomes intense enough to force hydrogen atoms so close together that their electrons can no longer remain bound to individual nuclei. Instead, the electrons become free to flow through the material, turning the hydrogen into a conductor of electricity. A metal in the sense of electrical conductivity, though it remains a fluid. This layer extends down tens of thousands of kilometers, perhaps all the way to the core. As Jupiter rotates, the metallic hydrogen rotates with it. But the layer isn't perfectly uniform or perfectly rigid. Convection currents flow through it, carrying heat from deeper layers upward toward the surface. These currents involve movement of electrically charged material, and moving charges constitute an electrical current. When you have electrical currents in a rotating, conducting fluid, you create the conditions necessary for a dynamo effect, and this is what generates Jupiter's magnetic field. The field isn't perfectly aligned with Jupiter's rotation axis. It's tilted by about 10 degrees, similar to the way Earth's magnetic field is tilted relative to Earth's rotation axis. This means that as Jupiter rotates, the magnetosphere wobbles slightly, sweeping through space like a rotating lawn sprinkler. This wobble affects the interactions between the magnetosphere and the solar wind, creating periodic variations in radio emissions and auroral activity. The magnetosphere itself is an enormous structure. It extends about 7 million kilometers sunward toward the Sun, where it's compressed by the pressure of the solar wind. On the opposite side, away from the Sun, it stretches outward into a magnetotail that can extend hundreds of millions of kilometers, sometimes reaching all the way to Saturn's orbit. This tail is constantly changing, buffeted by variations in the solar wind, sometimes breaking off and reconnecting in magnetic reconnection events that release tremendous bursts of energy. Inside the magnetosphere, trapped charged particles spiral along the magnetic field lines, creating intense radiation belts. These belts are the Jovian equivalent of Earth's Van Allen belts, but they're far more dangerous. The radiation levels near Jupiter are high enough to be lethal to humans within a matter of hours, and spacecraft passing through the inner magnetosphere must be carefully shielded to protect sensitive electronics. The radiation comes from electrons and ions, mostly protons, that spiral back and forth along the field lines, bouncing between the northern and southern hemispheres as they're trapped by the magnetic field's shape. The Galilean moons orbit within Jupiter's magnetosphere. As they move through this radiation-filled environment, they interact with the field in complex ways. Io, the innermost large moon, spews out about 1 ton of material per second from its volcanoes. Much of this material is ionized and trapped in Jupiter's magnetic field, forming a torus, a donut-shaped cloud of plasma that encircles Jupiter at Io's orbital distance. This Io plasma torus is a major source of the particles that populate Jupiter's magnetosphere. A particularly fascinating interaction occurs between Jupiter and Io. A tube of electrical current, called a flux tube, connects Jupiter's ionosphere with Io. As Io moves through Jupiter's magnetic field, it acts like a conductor cutting through field lines, inducing enormous electric currents. These currents flow along the flux tube from Io down to Jupiter's ionosphere, carrying power measured in trillions of watts. When the flux tube footprint hits Jupiter's atmosphere, it creates a bright auroral spot, a glowing footprint of Io visible in ultraviolet light. Europa and Ganymede also create footprints, though not as bright as Io's. The strength of Jupiter's magnetosphere makes it a powerful source of radio emissions. Jupiter broadcasts radio waves at frequencies ranging from a few kilohertz to tens of megahertz. These emissions were discovered in the 1950s, making Jupiter the first planet besides Earth known to emit radio waves. The emissions are generated by electrons spiraling around magnetic field lines, a process called synchrotron radiation. The intensity varies with Jupiter's rotation, with the position of Io, and with solar wind conditions. Spacecraft exploring the Jupiter system must navigate this harsh magnetic environment carefully. Voyager 1 and Voyager 2, which flew by Jupiter in 1979, were designed with radiation shielding around their most sensitive components. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, accumulated significant radiation damage over its mission, eventually losing function in some systems. Juno, currently orbiting Jupiter, follows a highly elliptical orbit designed to minimize time spent in the most intense radiation regions, diving in close to Jupiter for brief periods and then retreating to safer distances. The magnetosphere is not a static structure. It breathes, expanding and contracting with changes in the solar wind. Sometimes the magnetosphere can inflate to sizes even larger than its average 7 million kilometer sunward extent. Other times it compresses, shrinking the size of the protective bubble. These changes affect the trapped radiation belts, the auroras, and even the interactions with the moons. Understanding Jupiter's magnetosphere tells us about fundamental plasma physics, about how magnetic fields interact with flowing charged particles, about how dynamos work in planetary interiors. The same processes that create Jupiter's field occur in other giant planets, in rapidly rotating stars, even potentially in some exoplanets. By studying Jupiter's magnetosphere in detail, we're learning principles that apply far beyond our solar system. This invisible giant, this magnetic cocoon surrounding Jupiter, is one of the planet's most important features. It shields the moons from some of the solar wind's intensity, though it also subjects them to intense radiation. It channels particles into the atmosphere, creating auroras. It generates radio waves that we can detect from Earth. It's a structure larger than anything else in the solar system except the Sun's own heliosphere, and yet it's completely invisible to the naked eye, detectable only through its effects on charged particles and electromagnetic radiation. At Jupiter's poles, the night sky is never truly dark. Auroras glow there continuously, day and night, pulsing and shimmering in ultraviolet, X-ray, and infrared light. If you could somehow float above Jupiter's North Pole and had eyes sensitive to ultraviolet light, you would see a vast oval of luminescence circling the magnetic pole, with tendrils and curtains of light dancing and swaying as charged particles rain down into the atmosphere. These auroras are fundamentally similar to Earth's northern and southern lights. Charged particles, mostly electrons and protons, are channeled along magnetic field lines toward the poles. When they strike the upper atmosphere, they transfer their energy to atmospheric atoms and molecules, exciting them to higher energy states. When those atoms and molecules relax back to their normal states, they emit light. The color and wavelength of that light depend on which atoms or molecules are involved and how much energy they've absorbed. On Jupiter, the auroras are predominantly hydrogen-based. The atmosphere is mostly hydrogen, so most of the collisions involve hydrogen molecules or hydrogen atoms. When these are excited, they emit ultraviolet light. This is why Jupiter's auroras are most spectacular when viewed in the ultraviolet part of the spectrum. The Hubble Space Telescope has captured stunning images of Jupiter's auroral ovals in ultraviolet, showing bright, dynamic structures that dwarf anything Earth produces. The total energy in Jupiter's auroras is staggering. Earth's auroras, even the most intense ones, represent a power input of perhaps 100 gigawatts. Jupiter's auroras are hundreds of times more powerful, representing continuous power inputs, measured in terawatts. This energy comes from multiple sources. Some comes from the solar wind, particles from the Sun that are captured and accelerated by Jupiter's magnetic field. Some comes from volcanic emissions from Io, which populate the magnetosphere with charged particles. And some comes from Jupiter's own rotation, which drags the magnetic field around and creates electric fields that accelerate particles. The auroral ovals at Jupiter's poles are not uniform circles. They have complex structure with bright regions and dim regions, with arcs and spots and streaks. Some features are stable, persisting for hours or days. Others change rapidly, brightening and fading on timescales of minutes. High-resolution observations have revealed fine structure within the auroras, individual beams of particles creating bright spots where they hit the atmosphere. One of the most distinctive features of Jupiter's auroras is the auroral footprints of the moons. Io, Europa, and Ganymede, each, create a bright spot in Jupiter's auroral oval, marking the location where the flux tube connecting the Moon to Jupiter intersects the atmosphere. Io's footprint is the brightest, reflecting the intense electromagnetic interaction between Io and Jupiter. The footprint is not a single spot, but rather a complex structure with a main spot and trailing spots, showing where the perturbed magnetic field lines reconnect and where waves in the plasma propagate. Jupiter's auroras also emit X-rays. This was a surprise when first discovered because Earth's auroras don't produce significant X-rays. The X-rays from Jupiter come from highly energetic ions, particularly oxygen and sulfur ions originating from Io that are accelerated to enormous speeds before crashing into the atmosphere. These ions must be traveling at a significant fraction of the speed of light to produce the X-ray energies that have been observed. For years, the mechanism that accelerated these ions remained a mystery. Recent work combining data from multiple spacecraft has shown that electromagnetic waves in Jupiter's magnetosphere can accelerate ions through a process called ion cyclotron acceleration, essentially allowing ions to surf electromagnetic waves down into the atmosphere. The X-ray auroras pulse regularly, brightening every 27 minutes or so. This pulsation corresponds to oscillations in Jupiter's magnetosphere, driven by the rotation of the planet and by interactions with the solar wind. The pulsations are not perfectly synchronized between the northern and southern hemispheres. Sometimes, the north pulses while the south remains steady. Other times, both pulse together. This asymmetry is unexpected and not fully understood, but it suggests that the processes driving the X-ray auroras are more complex than simple mirroring between hemispheres. In addition to ultraviolet and X-rays, Jupiter's auroras emit infrared light. Infrared observations have detected emissions from ionized hydrogen molecules, specifically H3+ ions. These ions form when energetic particles ionize molecular hydrogen, knocking an electron free, and then that ionized molecule collides with another hydrogen molecule to form H3+. These ions are bright emitters in the infrared, and by measuring their emissions, astronomers can map the temperature and density structure of Jupiter's upper atmosphere at the poles. The infrared auroras extend over a larger area than the ultraviolet auroras. While the UV emissions are concentrated in a relatively narrow oval, the infrared emissions fill much of the polar region. This suggests that the particles responsible for the infrared auroras penetrate deeper into the atmosphere and spread out more before they deposit their energy. The temperature in the auroral regions is higher than in non-auroral regions, sometimes by several hundred degrees, indicating that the auroral processes are an important source of heating for Jupiter's upper atmosphere. Unlike Earth's auroras, which are most intense during geomagnetic storms triggered by solar activity, Jupiter's auroras are always on. They never stop. Even when the solar wind is calm, Jupiter's auroras continue to glow, powered by the planet's rotation and by particles from Io. During times of increased solar activity, when a coronal mass ejection from the Sun impacts Jupiter's magnetosphere, the auroras do brighten and become more dynamic, but they never turn off completely. The Juno spacecraft, which has been orbiting Jupiter since 2016, has provided unprecedented views of the auroras from close range. Juno's orbit takes it over the poles, allowing it to observe the auroras from above and to pass through the regions where particles are being accelerated. Instruments on Juno measure the energy, composition, and direction of particles as they plunge into the atmosphere. These measurements are revealing the detailed physics of how auroras work, not just at Jupiter, but at any planet with a magnetic field and atmosphere. One surprising discovery from Juno is that Jupiter's polar auroras, the X-ray auroras located inside the main auroral oval, can switch off abruptly on the night side of the planet. While the main auroral oval remains bright, the polar auroras within it dim dramatically when they rotate onto Jupiter's night side. This was completely unexpected. The mechanism is not yet understood, but it suggests that sunlight plays a role in sustaining these particular auroral features, perhaps by ionizing material in the upper atmosphere or by affecting the magnetic field configuration. Jupiter's auroras are a visible manifestation of the planet's magnetosphere. They show us where particles are entering the atmosphere, how much energy they're carrying, and how the magnetic field is structured. By studying the auroras, we learn about plasma physics, about magnetic field dynamics, about atmospheric chemistry. We also gain insights that apply to other planetary systems. Many exoplanets orbit close to their stars, where they experience intense stellar winds. Understanding how Jupiter's magnetosphere responds to the solar wind helps us predict how these exoplanets might respond to their stellar environments. The continuous light shows at Jupiter's poles are reminders that even a planet without a solid surface, even a world so far from the sun that sunlight is faint, can be a place of extraordinary energy and activity. The auroras never cease. They pulse and shimmer, brighten and fade, create structures and dissolve them, all driven by the invisible forces of magnetism and the endless rain of charged particles from space and from the volcanic moon, Io. We've talked about Jupiter's atmosphere, its bands and storms, its rapid rotation. We've discussed its magnetosphere and auroras, its moons and its place in the solar system. But what lies beneath? What exists in the thousands of kilometers between the cloud tops we can see and the core at Jupiter's center? This is one of the great unknowns in planetary science because we cannot see inside Jupiter directly. Everything we know about the interior comes from indirect evidence. Measurements of the planet's gravitational field, its magnetic field, its shape, its heat output, and theoretical models of how matter behaves under extreme pressure and temperature. Let's descend through Jupiter's layers, imagining a journey downward from the cloud tops toward the center. We begin in the visible atmosphere, where temperatures are around -110 degrees Celsius, and pressure is about 1 bar, roughly equal to atmospheric pressure at sea level on Earth. Here, ammonia ice crystals form the white clouds we see in the zones. The atmosphere is predominantly hydrogen and helium, with traces of other compounds. As we descend, pressure and temperature both increase. After 100 kilometers or so, we've reached a depth where pressure is about 1,000 bars, 1,000 times Earth's surface atmospheric pressure. Temperature has risen to around 1,000 degrees Celsius. At these conditions, hydrogen no longer exists as a gas. It has been compressed into a liquid. But this isn't liquid hydrogen like you might find in a cryogenic tank. This is supercritical hydrogen, a state where the distinction between gas and liquid blurs. The hydrogen is dense enough to be considered liquid, but there's no sharp transition, no surface where gas suddenly becomes liquid. It's a gradual change as you descend. Continuing downward, the pressure keeps mounting. At a depth of roughly 7,000 kilometers, pressure reaches about 2 million bars. Temperature is around 8,000 degrees Celsius. At these extreme conditions, hydrogen undergoes a remarkable transition. The pressure is so intense that it squeezes hydrogen molecules together until they can no longer exist as molecules. The atoms are crushed so tightly that electrons are stripped away, becoming free to move throughout the material. The hydrogen becomes metallic, an electrical conductor like iron or copper, except it remains a fluid, not a solid. This metallic hydrogen layer is thought to comprise the bulk of Jupiter's mass. It extends from about 7,000 kilometers depth all the way down to perhaps 60,000 kilometers or more, perhaps 3/4 of the distance to Jupiter's center. Within this metallic hydrogen layer, temperatures and pressures continue to rise. At the bottom of this layer, temperature might reach 16,000 degrees Celsius or higher, and pressure might exceed 45 million bars. Metallic hydrogen is a state of matter that doesn't exist naturally on Earth. It has been created in laboratory experiments for tiny fractions of a second under extreme pressure, but we've never been able to study its properties in detail. Most of what we know about metallic hydrogen comes from theoretical calculations and computer simulations. These simulations suggest that metallic hydrogen is an excellent conductor of both electricity and heat, and that it's a fluid with convection currents flowing through it, carrying heat from the deeper interior upward. It's within this metallic hydrogen layer that Jupiter's magnetic field is generated. As the layer rotates with the planet, convection currents create a dynamo effect, generating electric currents that produce the magnetic field we observe. The exact mechanism is complex and not fully understood, but the basic principle is the same as the dynamo that generates Earth's magnetic field, just on a much larger scale. Beneath the metallic hydrogen lies the core, or at least, we think there's a core. For decades, scientists assumed Jupiter must have a dense core composed of rock and metal, similar in composition to Earth, but much more massive, perhaps 10 to 20 times Earth's mass. This core was thought to have formed first, during Jupiter's early growth, and to have been the seed that captured all the hydrogen and helium that now makes up most of the planet. Recent data from the Juno spacecraft have complicated this picture. By carefully measuring tiny variations in Jupiter's gravitational field as Juno orbits the planet, scientists can infer the distribution of mass within Jupiter. The results suggest that Jupiter's core is not a compact ball of rock and metal. Instead, it appears to be diffuse, mixed with the overlying layers, extending outward to perhaps 30 to 50% of Jupiter's radius. The core might contain 7 to 25 times Earth's mass in heavy elements, primarily rock and metal, but these elements are not concentrated in a well-defined sphere. They're spread out, mixed with hydrogen and helium. Why would the core be diffuse? One possibility is that Jupiter formed with a more compact core, but over billions of years, mixing processes have gradually spread the core material outward. Another possibility, more dramatic, is that Jupiter was struck by a massive impactor, perhaps a planet 10 times the mass of Earth, during the solar system's early history. Such an impact could have disrupted the core, scattering its material and mixing it into the overlying layers. Evidence for this scenario is tentative, but it's one explanation for the observed structure. At the very center of Jupiter, conditions are almost unimaginable. Pressure might be around 100 million bars or higher. Temperature could be 20,000 to 30,000 degrees Celsius or more. At these conditions, even rock and metal would not behave as solids in any conventional sense. They would be compressed to densities far higher than on Earth, perhaps twice the density of Earth's core. The distinction between solid and liquid becomes meaningless at such pressures and temperatures. The material is simply dense, hot, and under enormous pressure. Jupiter emits more energy than it receives from the Sun, about 1.6 times as much. This excess energy comes from two sources. One is the slow release of heat left over from Jupiter's formation. 4.6 billion years ago, when Jupiter formed, gravitational energy was converted to heat as material collapsed inward. Some of that heat is still leaking out through the planet's layers, radiating into space. The other source is ongoing gravitational contraction. Jupiter is still shrinking, very slowly, at a rate of about 1 millimeter per year. As it shrinks, gravitational potential energy is converted to heat, warming the interior and contributing to the energy output we observe. This internal heat is what powers Jupiter's atmospheric dynamics. Unlike Earth, where weather is driven primarily by sunlight heating the surface and atmosphere unevenly, Jupiter's weather is driven mostly from below, by heat convecting upward from the interior. This is why Jupiter's atmospheric circulation is so vigorous despite the planet's great distance from the Sun. The jet, streams, the zones and belts, the storms and vortices, all are powered by heat rising from deep within the planet. The interior of Jupiter is a place of extremes. Pressures millions of times greater than anything on Earth's surface. Temperatures hot enough to vaporize any material we know. Hydrogen transformed into a metallic fluid. A diffuse core of rock and metal mixed with the surrounding layers. All of this hidden beneath thousands of kilometers of atmosphere and deep layers of liquid and metallic hydrogen, inaccessible to direct observation, known only through inference and theory. Understanding Jupiter's interior is important not just for understanding Jupiter, but for understanding how giant planets form and evolve. Every giant planet we've discovered around other stars, every hot Jupiter orbiting close to its parent star, every cold gas giant in the outer reaches of another solar system shares fundamental similarities with Jupiter. They all formed by accumulating gas around a solid core. They all have interiors dominated by hydrogen and helium. They all generate heat through contraction and radiate it into space. By understanding Jupiter's interior structure and evolution, we learn principles that apply to giant planets throughout the galaxy. Future missions may probe Jupiter's interior more directly. Proposed concepts include atmospheric probes that could descend deeper than the Galileo probe did, reaching depths of hundreds or thousands of kilometers before being crushed by pressure. Seismology, measuring vibrations traveling through Jupiter's interior, could reveal its structure in detail, much as seismology has revealed Earth's internal layers. For now, though, we rely on gravity measurements, magnetic field measurements, heat flow measurements, and theoretical models to piece together the structure of this hidden realm. The interior of Jupiter is a reminder that even for a planet we've studied for centuries, even for the largest planet in our solar system, there remain profound mysteries. We don't know the exact size or composition of the core. We don't know the detailed structure of the metallic hydrogen layer. We don't know precisely how deep the jet streams extend or how the internal heat is transported from the deep interior to the surface. Each measurement, each mission, each new analysis brings us closer to understanding, but Jupiter keeps its secrets well. We've journeyed through Jupiter's characteristics, from its formation billions of years ago to its present state. We've explored its rapid rotation, its banded atmosphere, its persistent storms. We've examined its 4 large moons, each a world unto itself. We've ventured into the invisible magnetosphere and watched the auroras pulse at the poles. We've descended, at least in imagination, into the planet's interior through layers of liquid hydrogen and metallic hydrogen down to a diffuse core of rock and metal. Jupiter remains, as it has for billions of years, the dominant planet in our solar system. Its mass is greater than all other planets combined. Its gravitational influence has shaped the solar system's architecture, scattering asteroids, deflecting comets, possibly preventing planets from forming in regions where it carved gaps in the early solar nebula. Every planet's orbit has been influenced, at least slightly, by Jupiter's gravity over the eons. The planet continues to change, though slowly by human standards. The Great Red Spot is shrinking, perhaps heading towards some new equilibrium size, or possibly toward eventual dissipation. New storms form and old ones fade. The atmospheric bands shift subtly in position and intensity. The moon Io continues its volcanic fury, spewing material into the magnetosphere. Europa's ice shell may crack and reform, opening and closing potential windows into the ocean below. Ganymede and Callisto orbit patiently, ancient and battered, witnesses to billions of years of solar system history. Jupiter's rotation continues, steady and fast, completing a day every 10 hours. The planet bulges at the equator, compressed at the poles, an oblate spheroid spinning in the darkness. The magnetic field wobbles as the planet turns, sweeping through space, channeling particles into the polar regions, generating auroras that never cease. The internal heat continues to leak outward, a slow release of energy that will persist for billions more years, until Jupiter has cooled and contracted to some final, cold equilibrium. Looking forward, Jupiter will remain a target of scientific exploration. Future missions will study the moons in greater detail, searching for signs of life in Europa's ocean, investigating Ganymede's magnetic field, exploring Callisto's ancient surface. Atmospheric probes may descend deeper into Jupiter's atmosphere, measuring composition and structure in layers we've never directly sampled. Seismology might reveal the interior structure with precision. And always, ground-based telescopes and orbiting observatories will continue to watch, to monitor the ever-changing atmosphere, to track storms and measure winds, to observe the moons and the auroras. Jupiter has been a part of human awareness for as long as humans have looked up at the night sky. Ancient astronomers tracked its motion across the constellations. Galileo's discovery of its 4 large moons changed our understanding of the cosmos. Modern spacecraft have revealed it as a complex, dynamic world, far more interesting than a mere point of light in the sky. And yet, for all we've learned, Jupiter remains mysterious in fundamental ways, its interior hidden, its atmospheric dynamics not fully understood, its moons potentially harboring secrets we've only begun to uncover. As you rest, as your thoughts slow and settle, Jupiter continues its orbit around the Sun, 5.2 astronomical units away, taking nearly 12 years to complete one revolution. It spins. Beneath its cloud bands, radiates heat into the void, generates its magnetic field, sustains its auroras. It is patient, ancient, enormous, a world of hydrogen and helium, of storms and lightning, of moons and rings, of mysteries and wonders. The universe is full of such wonders, and Jupiter is one of the most magnificent we know. Not the largest planet possible, Jupiter is about as large as a planet of its composition can get without becoming something else, without adding enough mass to ignite fusion and become a star. But large enough to dominate its region of space, to shape the system around it, to capture our imagination and our scientific curiosity. If you've been listening to this journey through Jupiter, if these facts and figures and descriptions have accompanied you through the past couple of hours, thank you. Whether you've stayed awake through all of it or drifted off somewhere along the way, I hope you found some measure of calm in the contemplation of this distant giant. The universe is vast and strange and beautiful, and Jupiter is one small part of that vastness, spinning quietly in the outer solar system, ancient and magnificent. If you enjoyed this exploration, if these cosmic details brought you some peace, please consider liking this video and subscribing to Nebula Nights. There are many more worlds to explore, many more quiet journeys to take through the cosmos. Until next time, rest well.